the 120 kilowatts lithium power milestone. NASA just vaporized the previous record for electric propulsion by pumping 120 kilowatts through a single lithium-fed plasma engine. During a February test at the Jet Propulsion Laboratory that was just fully declassified this month, a prototype thruster produced a vivid red plume of ionized metal while its internal electrode glowed white at 5,000 degrees. This isn't just another incremental gain. It's a 25-fold power jump over the thrusters currently pushing the Psyche mission toward the asteroid belt. And the secret to this massive leap lies in the physics of a liquid metal propellant, lithium as the ultimate propellant. Traditional electric engines like Hall thrusters rely on noble gases like xenon, which are stable but expensive and physically bulky to store. Magnetoplasma-dynamic, or MPD thrusters, take a more violent approach. By using lithium, we are essentially turning a metal into a supersonic blowtorch. Inside the chamber, an enormous electrical current is passed through lithium vapor, creating a plasma that is then shoved out the back by its own magnetic field. This is the Lorentz force in action. Because lithium is so light, you can accelerate it to extreme exhaust velocities, roughly 100 kilometers per second. That is 20 times faster than the chemical fire coming out of a Falcon 9. The strategist's view here is mass efficiency. You can carry 10 times the payload with 90% less fuel mass. This transition from gas to metal propellants solves the storage density problem that has haunted long-distance mission planning for decades. And while the physics are elegant, the thermal reality is a different story. The 5,000-degree hurdle. Dealing with 5,000 degrees Fahrenheit is the ultimate engineering bottleneck. At these temperatures, the tungsten electrode is effectively a sun in a bottle, and the vacuum chamber at JPL had to be water-cooled just to keep from melting. Proving these components can survive for 23,000 hours is the next mission-critical milestone. Scaling toward megawatt-class missions, the 120 kilowatt milestone is a proof of concept, but a crewed Mars transit requires megawatt-class architecture. NASA's current roadmap calls for scaling this design to between 500 kilowatts and 1 megawatt per individual thruster. To move a crewed ship, you would cluster 4 of these units together, powered by a space-hardened nuclear reactor. This is the move from solar electric to nuclear electric propulsion. It moves us away from being slaves to the sun's energy and toward a high-thrust system that can push through the deep dark of the outer solar system. The end of the Hohmann Transfer. The real takeaway from the JPL results is that we are witnessing the end of the Hohmann Transfer era. For 60 years, mission planners have been forced to wait for specific planetary alignments every 2 years because our chemical rockets lacked the raw power to fight orbital mechanics. By mastering 120 kilowatts of lithium plasma, NASA is laying the groundwork for continuous thrust trajectories that could eventually shrink the Earth-Mars transit to 30 days. This shifts the mission profile from a desperate survival sprint into a sustainable supply chain. For the aerospace engineer, the priority is no longer just building a bigger tank. It is about building a better radiator and a more stable nuclear core to feed the engine. The era of the one-shot mission is closing, replaced by high-power infrastructure that treats the solar system like a logistics network. Watch for the next milestone in late 2026, when the first 500-kilowatt endurance test begins at the Glenn Research Center. Subscribe for more.